Good morning. Today we are going to present the biomechanical analysis of the knee flexion-extension movement. To perform this analysis, we followed a rigorous experimental protocol in the bioengineering laboratory. Our objective was to capture the kinematics of the lower limb during a gait cycle. We placed passive markers on specific anatomical landmarks defined by the standard biomechanical model. Specifically, we located markers on the hip, in the lateral and medial Epicondyles of the knee, and the lateral and medial Malleoli of the ankle. And why these points? Because they allow us to define the joint centers mathematically. For example, the knee center was calculated as the midpoint between femoral epicondyles, and the ankle center was calculated as a midpoint between the malleoli. This geometry is crucial because it allows our code to reconstruct the femur and tibia as rigid segments in a 3D space, which is the foundation for determining the range of motion.
Once we obtain the raw coordinate files from the experiment that we made in the lab, we process them using our Python algorithm. The core of our code is the construction of a local coordinate system, or SCLs. We did not use global coordinates for the angles. Instead, we implemented a function called create a local system. Inside this function, we use vector algebra to define an orthonormal basis for each segment. So let me explain. First, we design a y-axis as the longitudinal vector connecting the joint centers. And second, we use a cross product between the y-axis and a gait vector to obtain the x-axis pointing anteriorly. Finally, a second cross product gave us the z-axis, which represents the extension axis of rotation. So here we have an orthonormal basis to work with. With these reference frames, we calculate the rotation matrix of the shank relative to the type. To extract the specific flexion angle, we decompose this matrix using Euler Angles with a ZXY configuration or rotation sequence, isolating the Z component, which corresponds to the clinical flexion we are analyzing.
A major challenge we faced was a signal noise and artifact, or rather that showed an initial period of static silence, and more importantly, a significant outlier peak that exceeded the normal biomechanical range by over 30%. Instead of just deleting that data manually, which isn't good practice, we wrote a code to fix it properly. First, the program automatically detects when the movement starts and cuts out the silence at the beginning. Second, that outlier peak. This code fins and smooths it down to a normal level, making sure the move looks continuous. For theoretical comparison, we move beyond simple guessing. We use SciPy optimized curve_fit library. This algorithm applies the least squares method to interactive thousands of times, adjusting amplitude, frequency, phase parameters until it finds the ideal sinusoidal model. Then mathematically minimize the error. Finally, let's look at the results. In this graph, the blue line represents our process experimental flexion angles, and the red dashed line is the optimized theoretical models. I required we calculate the Pearson correlation coefficient before optimization. Our raw data showed a poor or even negative correlation due to phase shifts. However, after applying our phase looking and optimization algorithm, we achieved a final R value of 0.84. This high R value validates our procedure. It proves despite experimental artifacts, the subject Gait follows a harmonic sinusoidal pattern consistent with bibliography. We successfully applied programming concepts to solve a real-world bioengineering problem, transforming raw coordinates into meaningful clinical data. Thank you.